what we're actually going to study today is essentially how does parasitic capacitance affects the performance. In a previous lecture, we studied how the metallization loss affects the performance of the inductor. And here, we're actually going to see how the finite parasitic capacitance actually affects the performance. So this is the same inductor we have used before. It's a 5 nanohenry device. It has an assumed series resistance of 6.3 ohms, which in this model is assumed to be constant up to 2 gigahertz, and then it increases as the square root of the frequency. And then it has a parasitic capacitance of the substrate, given as Cp, and a parasitic capacitance between its turns, given as Cs. So what those lines really give you is the quality factor of this inductor as a function of frequency. And there are lots of interesting things to observe here. First of all, this line right here, this blue line right here, is drawn for a capacitance to the substrate of 75 femto and series capacitance of 9 femtofarads, which I would say are fairly typical numbers. And what you will see is that in this case, you're hitting a maximum Q of about 10, which is again very typical for an RFIC inductor, and a self-resonance frequency of about 8 gigahertz. What is really interesting to observe here is that as you decrease the parasitic capacitance, and let's take this case here, if I decrease my parasitic capacitance by 80%, the Cp, and I also decrease my Cs by 60%, then, as you probably would imagine, the resonant frequency shifts to the right. So it actually goes from 8 to practically 17 gigahertz, which is actually a dramatic increase. Now that means you can use this inductor for a far wider range of frequencies than you could use the original one. But what you might not have expected necessarily is not only the self-resonance increases, but the maximum Q increases as well. In fact, the maximum Q goes from 10 to about 17. And that basically means that this is a better inductor for a wider range of frequencies. It's not just the same inductor for a wider range of frequencies. It's simply a better inductor. It has basically a higher Q. And the reason behind that is because as you're decreasing these capacitances, you're increasing the reactance of the inductor. And the reactance actually increases as a function of frequencies, linear, is J omega L. But the resistance usually increases as a function of the square root of the frequency. And so that means that the Q that depends on the ratio of the two will actually increase. And that's why that you observe this trend here. So what's really interesting about this is it gives you essentially the two benefits that you will get if you can dramatically reduce those two capacitances. And we'll see in a next video how you can reduce those capacitances, primarily by employing micro-machine techniques. The same information is actually shown in this graph, where essentially here I'm showing you the reactance instead of the Q. So this is the X of the inductor. And you can see again what I mentioned before, that as you are basically decreasing your capacitances, let's say by 80 or 60%, how essentially you're shifting the resonant frequency to much higher frequencies and the value of the X.